Bam! Mr. Tarrou. In this lesson, we are going to be introduced to the concept of the distributive property, a skill that you are going to have to know from pre-algebra, algebra, geometry, algebra 2, trig, pre-calculus, calculus. It is a skill that never goes away. It'll help you simplify expressions, solve equations. It'll help you when you learn how to graph ellipses and circles and these things called conic sections to put those equations into standard form and then back out of standard form. It has tons of applications because you use it basically from here on out in your math studies. So let's see what it says. Let A, B, and C be real numbers. And what we're going to be looking at is a term. It might be a number, might be a variable. It could be a collection of numbers and variables that are multiplied together and they're in a single group. And terms are separated by addition and subtraction. So at least in the standard sort of basic formula, if you will, we have one term being multiplied into a grouping of two terms. But you could have three terms in here. You could ultimately, as we get up through your algebra studies, have two polynomials that you're multiplying together where there's a couple of, there's like two parentheses that are touching, and everything has to connect through multiplication. And you know it's multiplication because this letter A is touching the parentheses. There's not a plus or a minus sign in between them, and we'll take care of that in these 6 examples, I think there are, or 5, that are on this video. My textbook shows 4 different versions of the distributive property. If you have a term that is touching the parentheses getting multiplied through, it doesn't matter if it's positive or negative or plus or minus, but it is A times B plus A times C or A times B plus A times C. So each of these lines that I'm putting in here, now this isn't standard notation, this is just me helping you see the connections. Each of these lines represents multiplication. And then my book writes a second version of that where the item being multiplied or touching the parentheses is at the end of the parentheses, and it's B times A plus C times A, or B times A minus C times A. I will, regardless of where my item is that is getting multiplied through the parentheses or touching the parentheses, I will always put what I'm multiplying in second and not first. That'll help. It helps my students know that they are avoid sign errors and maybe not accidentally add or subtract when they're supposed to be multiplying, or have a negative where they're supposed to be positive. So here we have a big rectangle. Now this isn't a proof of the distributive property, it's just to validate at least in one example that it actually works. To find the area of a rectangle, it's height times base, or length times width. And we have a height of 4 and a length of 3 plus 5. Well, 3 plus 5 is equal to 8, and indeed 4 times 8 is an area of 32 square units. That little exponent of 2 represents a unit of measure for area because there's length and there's width. And I can just see 4 times 8, there's 32, well, let's call them squares. They're not really squares, but we have an area of 32 square units. Well, this is highlighted in red and yellow, and if I pull that apart, I have a smaller rectangle, which is 4 times 3, and another rectangle, which is 4 times 5, and the area of that is 4 times 3, which is 12 square units. And then I have another area of 4 times 5, and 4 times 5 is 20 square units. Well, this area of 12 plus this area of 20 comes out to an area of 32 square units. And so whether I did 4 times 8 to get 32, or I did 4 times 3 to get 12, and 4 times 5 to get 20, I'm getting the same area, the same answer of 32 square units. So 4 times 3 plus 5 is equal to 4 times 3 plus 4 times 5. And it's an example, not a proof, but an example of how the distributive property actually works. Now over here I've got 3 examples. I have 2 times x minus 6, and we can see that that 2 is touching the parentheses, and thus that value of 2 is getting multiplied through. Now you'll notice that I circled a 2. That's in case the number is negative. You remember, I always circle what I'm multiplying through the parentheses to make sure that I don't forget that sign and get an incorrect answer, even though I know the basic steps for doing the distributive property. And that's going to be 1x. And by the way, if you have a variable with no number out front, there is said to be a coefficient of 1. Don't forget there's a 1 there. So you might want to just add that in. And by the way, a coefficient is just a number. It's what we call a number that's sitting in front of a or a group of variables. So we have 1x times 2 minus 6 times 2. And I always, again, with the issues with signs, I always wrap those values that I'm multiplying by in parentheses to make sure that you see that it's multiplication and not accidentally think that it's addition. So 1 times 2 is equal to 2, and don't forget the x. And negative 6 times 2 is equal to negative 12, so that problem is done. And negative 6, now I'm saying negative 6, if I leave that x times 2 up there, you might say, and correctly, that we have 2x minus, all right, so let's look here. You might say that this is 2x minus 12, and that would be absolutely correct. Well, if I cover up the 2x, and you just saw that little dash with the 12, you probably would read what? Negative 12. Well, a negative sign and a subtraction sign, they're really kind of the same thing. Now, they're not the same button on the calculator, but they mean the same thing as you look at this. That's a minus 12, or excuse me, a negative 12, or it's 2x minus 12. That's how I will generally write. I don't usually do like a plus negative, even though when you first start learning how to work with signs, that honestly sometimes is easier. But as you move through algebra, you don't want to keep writing plus minus. So, you know, use the plus negative as long as you need to, and that you're as you're learning to deal with adding and subtracting values that have different signs. But ultimately, we're going to move away from that, and just write the minus. Here we have negative parentheses, negative 3x plus 7. Well, there's no number there. But there is a number there. Whenever you have just a negative in front of parentheses, put a 1 in between there, between the negative sign and the parentheses, so that you can see that what you're actually multiplying through the parentheses is that negative 1. Now, if I were to write the a in the front, obviously it's correct, but what I'll see students doing is I'll write negative 1 times negative 3x, and then, well, is there a plus there? That's technically correct, because I wrote a plus, but then I'm bringing in a negative. Sometimes students, though, will forget to write the negative sign there, because they see the plus, so they'll just write plus and then the 1. They'll forget the negative is there. Or they'll do some kind of other weird, strange combination of signs and get a wrong answer there. Or they'll write this out, and then as they're doing their work, they'll forget there's a negative sign there, and they'll see negative 1 and maybe a negative 7 and write negative 8. Yeah, that's why I don't like putting the a in the front. Also, to just make sure that there's not a little dot there that you wrote for multiplication that then you forgot was there, wrap all the factors in parentheses to make sure you don't make any sign errors. Also, once you're in algebra, right, writing an x for multiplication is not a great idea because it looks like a variable. And then students think there's an extra variable in there that isn't really a variable, but it meant multiplication. So all these little issues, and I'm sure there's other examples that kids can come up with, are why I like to write the term that's in this binomial first, then leave a parentheses for the a that's getting multiplied in, and I don't have to write so many parentheses. It's easier to recognize what's being multiplied and not, and also just leads to fewer sign errors. So we have negative 3 times negative 1, which is positive 3, and positive 7 times negative 1, which is negative 7. And that problem is done. Bam! Okay, one last example. I'm just going to make sure I'm not running out of time here. Good. Is 4x minus 21 over 7. Now, I'm just introducing the distributive property for you, so I'm going to do this a little bit differently than maybe I would do on a normal basis, and I'll explain that at the end of this example. But we have 4x minus 21 over 7. If you want to, basically what I want to do with this is I want to rewrite this so that there's not one big fraction, but separate them into two separate fractions. And technically the directions for all of these are to simplify. So I can take this 7 that's in the denominator, pull it out front, and write 1 over 7 times, and then a fraction bar is a grouping symbol. So I need to take that 1, I have to have a 1 over 7 because the 7's in the denominator. I can't just write 7 because then That's kind of like a multiplication of 7, but this is a division of 7, right? So that would not be right. So leave the 1, or put a 1 on top and leave that 7 pushed down in the denominator. And I need to wrap this in parentheses, 4x minus 21. That is an equivalent notation to this fraction. It also now shows me that I need to take this 1 over 7, it's touching the parentheses, so we need to multiply that through the parentheses and get 4x times 1 over 7 minus 21 times 1 over 7. And it's not a good idea to work with fractions when everything doesn't look like a fraction, because the numerators and denominators need to line up. And do you need common denominators, or are you just simply multiplying across a fraction? It can get a little confusing. So let me put a 1 underneath the 4x and the 21, and we can see, okay, it's 4x times 1. So that's 4x. And it's 1 times 7, which is 7. And it's 21 times 1. And it's 1 times 7. And it's a negative times a positive, so it's negative. But 21 over 7, that's a fraction that's reducible. I can divide the numerator and denominator, if I had enough room, by 7, and 21 divided by, shouldn't really make your work go up, but I'm running out of room. 21 divided by 7 is equal to 3. And 7 divided by 7 is equal to 1. And I can, by the way, write that as simply just minus 3 as well. But we end up with 4 over 7x minus 3 over 1. That is how I can take this fraction with 2 terms in the numerator and split it apart to be 2 separate ones. And as you get more complicated algebraic problems through your studies, understanding this process will be very helpful. But we can also have at this point an alternative version of doing this problem by simply knowing how do we add and subtract fractions. Now, see, I wouldn't normally do my work this way for separating this fraction into 2 separate parts. I'm just doing it for this video because I'm specifically introducing the distributive property. When you add fractions like 2 over 3 plus 5 over 3, and I've written it so we already have common denominators, you simply add the tops together. We have 2 plus 5 is equal to 7 over the common denominator of 3. And actually, to bring my point together even more, let's write this as 2 plus 5, and then write it as 7 over 3. Because I don't really care about the answer being 7 over 3. What I want you to see is, what I'm kind of doing with this problem is sort of undoing or separating the subtraction. If I have 2 over 3 plus 5 over 3, common denominators already, I add the tops together and look, the 2 numerators that were in separate fractions are now in 1, and the common denominator I just copied. So if I look at this and going backwards, one term in the denominator with the addition sign, 2 terms in the numerator, I can go this way and give each term its own common denominator and do the reverse of adding fractions and pull them apart. Well, what do I have here? I have 1 term in the denominator and 2 terms in the numerator. So I can pull it apart and give each term in the numerator its own denominator. And so we can pull this apart with our knowledge of how to add and subtract fractions as well and get 4x over 7 minus 21 over 7. Now clearly this is a lot quicker than trying to use the distributive property to pull this apart. But again, every skill that you learn in your math book is there for a reason. It's because you're going to need to know how to do that skill later on in your studies, even though maybe there's a quicker way to do the problem. 21 and 7, these are both divisible by 7. And again, reducing that fraction, we get 21 divided by 7 is 3, and 7 divided by 7 is 1. And clearly we can write that as 4 over 7x minus 3, because dividing by 1 doesn't, well, it does something, it gives you the same answer back. So that is the end of my first 3 examples. I have got, 2 or 3 more to do. So let's get to them. Bam! Write the formula for the area of the triangle. So we have a triangle. It has a bunch of numbers and expressions on it. We have a value of 6, 5, and an expression which is equal to, or is, 6x minus 3. Now, we're not going to be able to actually find the area of this triangle because I don't know how long the base is. It has a variable in it. But I do know that the area of a triangle is 1/2 base times height. So it's going to be equal to 1/2 the base. Okay, now when you look at a triangle, the base isn't necessarily the bottom, even though we like to draw it that way. When you try to find the area of a triangle, the base and the height have to be two measurements which are perpendicular to themselves. So if I were to give you like a right triangle that's sort of like in this type of situation, the base, if you will, or what's at the bottom is a point, but you have two sides which are perpendicular. So this could the two legs of a right triangle, as an example, are always going to act as your base and your height. And multiplication is commutative, so it doesn't matter if you say this is the base and that's the height, or that's the base and that's the height. The point is they're perpendicular to each other. So when you look at this diagram, the bottom isn't necessarily the base, but I do have a marking which is perpendicular. So this is going to act as the base, so it's going to be 6x minus 3. And now we have the height. Well, I kind of already gave it away that this is perpendicular, but some students will accidentally use the 6 as the height. But when you measure your height on the wall, you don't put, your parents don't put a mark on the wall, or yourself, and then go down at an angle. You might be like 20 feet tall if you went slanted enough. You have to go straight down, straight perpendicular, 90 degrees to the base, or if you're measuring your height, to the floor. Unless somehow you can stand on the wall and do it sideways. But the point is here, this is going to be 5. The 5 is the height, not the 6. All right, so now we've got 1/2 times 6x minus 3 times 5. How about we go ahead just to, again, emphasize that use of the fractions with you guys, which so many students try to avoid, and do the 5 times, and let's make that 5/1 times the 1/2. So 1 times 5 is 5. 2 times 1 is 2. That is getting multiplied by 6x/1 minus 3/1. Now, I'm making everything look like a fraction so I can have all the numerators and all the denominators lining up and hopefully not make a mistake. So as we put this through, the 5/2 is touching the parentheses, and that means that all of that 5/2 is getting multiplied through the parentheses. We get 6x/1 times 5/2 minus 3/1 times, again, 5/2. I like to, especially since I'm doing this without the aid of a calculator in front of you, I like to do any kind of cancellation opportunities I have before I do the multiplication. It keeps the numbers smaller. And the 2 and the 3 and the 1 and the 5 don't share any common factors that are going to be helpful except for 1, which dividing by 1 does not change the value, so it's not very helpful. But 6 has a factor of 2, and so does 2. So 2 divided by 2 is equal to 1, and 6 divided by 2, you can do this because I'm going across a multiplication. 6 divided by 2 is going to be equal to 3. So now with my reducing done, or my cancellation done, I can have 3 times 5 is 15x. And don't forget the x. And then we have 1 times 2. I almost made a mistake there. 1 times 2, no. 1 times 1 is equal to 1. And I'm going to write that as a fraction just for practice and just to make sure that I keep all these numerators and denominators lined up. Negative 3 times 5. Or you can just say, here's a negative fraction being multiplied by a positive one. And negative times positive is negative, and get it out of the way. And then you can just say, well, 3 times 5 is 15. And 1 times 2 is equal to 2. If you don't look at that whole negative fraction times this positive fraction, some students will accidentally do negative 3 times 5, which is negative 15, and negative 1 times 2, which is negative 2. Well, negative divided by negative is positive, and that would give them a sign error. So it might be better just to say, hey, I got a negative fraction, a positive fraction, and negative times positive is negative, and then just again multiply the numerators and denominators separately with mental math, not your calculator. You need those skills as you move up through the math, through your math, and just in life in general. Now this is all equal to the area, which I can write A is equal to 15x minus 15 over 2. But I can also recognize and use a little function notation. I'm not sure if you've been introduced to that yet, but the only variable over here is x, which is the independent variable. Whatever x is going to determine the overall area of this triangle. So I can say that I'm finding the area in terms of x because that's the only variable on the right side of the equation. And now I am talking about an equation because I'm writing an equal sign. That's 15x, because dividing by 1 doesn't sort of really do anything. And then 15 over 2 is a mixed fraction, is 15 divided by 2. We can put 7 of those in there, which is 14. Leaves me with 1, and then not going straight to a decimal, that's 7 and 1/2, what I'm dividing by. Because I would not let my students in an Algebra 1 or pre-algebra class use calculators, and I would want to see that as a mixed fraction or an improper fraction, but not a decimal. 2 more examples coming right up. 6 less than the difference of -5 and 7y decreased by 1/4 of the sum of 12y and 16. Write the expression and simplify. Okay, write the expression. Oh, word problems. Oh, I'm so scared. Okay. Less than. Less than means to subtract, and if I have, let's say, $5 and someone has 2 less than me, then that person has 5 minus 2, not 2 minus 5. So when you see less than or more than, make sure that you turn the rest of that problem around. So we have, let's see, what color can I use here? We have 6 as a number, less than a subtraction, the difference of. Well, that tells me that I've already talked about 6 less than something else, and that something else is a difference of. These 2 words together will difference again mean subtraction, but difference of together means that I'm also going to be looking for some kind of, or needing to set up some kind of parentheses. So it's a difference of -5, so there's another number, and that's the other sort of thing that we're combining with subtraction here, 7y. So 6 less than, oh, the directions. Write an expression, oh, I said that. Write an expression to simplify. So 6 less than the difference of -5 and 7y. So the difference of -5 and 7y. I don't know if you just heard that, but that was a squirrel falling off the bird feeder outside. So the difference of -5 and 7y, and we're doing 6 less than that. Okay, let's keep going. Decreased by 1/4. Oh, so there's more going on. Okay, so then decreased by is yet another negative. I want to do all these negatives in this expression because, well, that opens up the opportunity of sign errors. And I want to point out that, you know, how you don't want to make those and how you avoid it. So decreased by 1/4. Well, at least in the U.S. money system, 4 quarters make up $1. So if I said 1/4, that's a hint that it's 1/4. But 1/4 is a multiplication of 1/4, dividing by 4. So it's a decreased by 1/4, again, of the, let's see here, sum of. So sum is addition, and then sum of means that it's a collection. It's a sum of a couple of things. So we're looking for some kind of addition. And again, that needs to be wrapped up in parentheses. So we're decreasing by, I don't know why I did that in yellow, decreasing by 1/4, 1/4 of the sum of, so parentheses with an addition inside, and what we're finding the sum of is 12y and 16. Okay, so not not the simplest examples of turning, of example of turning words into an algebraic expression, but at this point, hopefully we can handle some more difficult ones. Well, order of operations says, please excuse my dear Aunt Sally, work in parentheses. Well, inside this parentheses, we don't have anything that can go together. We don't have any like terms. And there's a -6 now. We're going over what? The distributive property. But this -6 that's a minus sign in between the 6 and the parentheses. If it was touching, then we would have to take the 6 and distribute it through the parentheses. But it's separated. That constant is separated from the parentheses by subtraction, so that -6 is not going through the parentheses. Now there's nothing out front, there's no exponent, and there's no division. So really these parentheses, in this particular case, aren't going to do anything. So -5 minus 7y minus 6. Now we do have a -1/4 going through those parentheses. And again, that negative sign needs to go through there, otherwise you'll have a wrong answer. So a sign error. So we have 12y, and it's a positive 12y. There's nothing out front, so it's plus 12y times -1/4 plus 16 times -1/4. And now I've got whole numbers and fractions, so just to make sure that I keep all this lined up correctly, let's put that over 1 so I can see how the numerators and denominators line up. We get -5y, -5 minus 7y minus 6. Now we have some reducing opportunities here. We have 12 on top and 4 on the bottom. I've actually been doing a lot of reduction ahead of time. Let's switch it up this time and actually just multiply this together. Positive 12 times -1 is negative, or a positive fraction times a negative fraction is negative. And then we have 12 times 1, which is 12y, and 1 times 4, which is 4. Now over here, we have a positive fraction times a negative fraction, so that's going to be negative. Or you could do 16 times -1 and see that it's -16, whatever works best for you for not making a sign error. And then 1 times 4 is 4. Same turned on. And now we have -5 minus 7y minus 6, -12, or actually let's just leave that negative there. 12 divided by 4 is 3y, and then 16 divided by 4 is 4. And again, make sure your signs are correct. Now we have some like terms together, which is why the next video is going to formally introduce like terms and combining them, knowing how to recognize them. I just thought that was a bit much for one video, so here I'm getting a little bit of overlap. But of my 5 terms, 1, 2, 3, 4, 5 terms, a collection of numbers and variables being multiplied together, or just a number, those like terms have the same variable, and they therefore also must have the same exponent. So this term has 1y because there's an exponent of 1, which isn't written, it doesn't need to be. This term has 1y. I'm wrapping them in circles because I want you to see that these negatives need to be combined. Or you can rewrite this if you'd like. -5 minus 6 minus 4 minus 7y minus 3y. You might be thinking, whoa, 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 all these are subtraction. Subtraction is not commutative. And maybe it's a little bit confusing with this one because everything is negative, but you can move terms around as long as you keep the sign with that term. Like 5 minus 3, well, that's equal to 2, but 3 minus 5 is -2. That's wrong, at least not if this is what it's supposed to be. But if I turn it around and I write -3 plus 5, I keep that 5 positive, not negative, and I keep the 3 negative, not positive. So I'm moving the terms around, but I'm moving the signs with them. Then I'm still going to get a right answer. -3 plus 5 is +2. So can't see it here with all the negatives, but you can move terms around as long as you take the signs with each of those individual terms. That's not the commutative property. That's just reordering your terms. So -5 plus a -6, or -6, is -11, and -11 minus 4, or -11 plus -4, is -15. And here again we have, actually I would, in class I wouldn't write this too many times, I would just sort of do this where it's like, hey, we're bringing these like terms together. Negative 7 minus 3, or negative 7 plus negative 3. Negative 7 minus 3 is negative 10y. Let me just check my answer. It looks good. Thank you for sticking with me. Got one more example. Woo! Last example. Oh, so sad. The recommended heart rate for exercise in beats per minute is given by the expression of 0.8 times 200 minus y, where y is a person's age in years, so that's really important that they're giving you this expression, and then right here they start telling you how to read it. Y is simply someone's age in years, not months, not days, not hours, not seconds, but in years. Rewrite the expression using the distributive property. And then without a calculator, find the recommended heart rate for someone who is 30 and someone who is 60. And they're just giving you the two numbers so that you can compare the heart rate from a, maybe you might consider this still an old person, but a younger person of 30 as opposed to someone who is 60. So we have the expression of 0.8 times 200 minus y. Okay, the distributive property. The 0.8 is, of course, touching the parentheses, which means that it needs to get multiplied through there, and we get 200 times 0.8 minus y times 0.8. Both of those are equivalent. I just want to write them together so that you don't really need to write the 0 point. You can just write 0.8. It's the same thing. So now we've got, well, what do we got going on here? Really, even though this is 3 digits, it's really just 8 times 2. Well, 8 times 2 is 16, and then 2 more zeros, but it's not 8 times 200, it's 0.8. So since there's one decimal there, we need to take the decimal that we see at the end of the 1600 and move it back one, and realize that 0.8 times 200 is 160. And then we have a negative times positive is negative, and there is a 1 in front of that y. 1 times 0.8 is 0.8, so we have negative 0.8 y, and there's our expression. This is actually a much easier question than the last one. It's just, hopefully you're not one of those students that just see, oh my god, so many words, or oh my gosh, so many words. Just skip it. Well, actually, it ends up being a very simple problem. So that was a straightforward distributive property, except for the decimal. We want to find the recommended heartbeat for someone who is 30. All right, well, if they're 30 years old, let's put that unit measure there. Okay, so for someone exercising, not resting heartbeat, that should be around 60, 70 beats per minute. But if they're exercising, the recommended heart rate, to build cardiovascular fitness and whatnot, is going to be 160 minus 0.8 times 30. Well, again, I wanted to be able to do this very easily in front of a camera, so I didn't pick like 27 years old or something like that. 30, there's a 0 at the end again. So 8 times 30 is 24, bring in another 0, because it's not 8 times 3, it's 8 times 30, it's a tens place. But again, there's a 0.8 there, so that one decimal place means we need to move that back 1, and really it's 24. And then minus 160. All right, so 160 minus 20 is 140. I always do my mental math from left to right for addition, subtraction, and multiplication, so I don't have to do the whole borrow and carry over type stuff. So 160 plus 20 is 180. Oh, excuse me, we're subtracting. Let's try that again. 160 minus 20 is 140, and then 140 minus 4 is 136. So 136 beats per minute. And then for someone who is 60 years old, then that is going to be 160 minus 0.8 times 60. 0.8 times 60 is going to be 48. Take that away from 160, so 160 minus 40 is 120, and 120 minus 8 is 112 beats per minute. So someone who is exercising who is 60 years old is not going to really maybe necessarily want to get their heart rate up. They shouldn't be getting their heart rate up, at least not by this recommended formula, as high as someone who's in their 30s or certainly 20s or well, your age of whatever it may be, teens, or I don't know what your age is that you're studying this. But at any rate, the older we get, the lower our recommended heart beat is for exercise. Anyway, that is 6 examples now. That's a distributive property. I'm Mr. Drew. I hope I've helped. Go do your homework.